Okay, this is patch a day number 13. Hopefully it's not unlucky. I guess anything could be unlucky. You just the way you look at it. This is going to be about how to turn an image into sound. I think I've done something like this in the tutorials. And yes, there's sort of a couple different ways of doing it. It's about a zillion different ways of doing this. jit.qt.movie is where we want to start. Playing back a movie. I guess we could give it some arguments for the size, 640 by 480. Very good. Make a message to read a video. This time we're going to read a video called track2.mov, just because it's got some grooviness or some stuff that will work well. I didn't mean to make a message there. Make a new object for the metro, and I guess we'll give it 30 millisecond time between ticks, bangs, and we'll turn it on with a toggle. And hook it up. I suppose we could do, for the moment, just put a little P window in here so we can see the video. Click that message and turn it on, and we can see we'll be creating some sound according to this disco floor video going on here. Alright, there's a couple different ways of doing this, either using frame differencing to only output things when the video, according to the way the video changes, which actually makes sense in terms of sound, because sound is something connected with change, and therefore doing that makes sense. But this time we're going to actually just analyze the entire video frame to do something with it. First thing I'll put in here is a jit.change, just to make not do any unnecessary processing. Don't process frames that are the same. And then jit.rgb, this should just make RGB to Luma, sorry. That'll just make the whole thing a little bit leaner and meaner, and discard all the color information. Then we'll make the matrix smaller. This is actually unnecessary maybe, but we'll give it a name, the matrix, jit.matrix blammo. That'll be, for some reason, we'll see in a couple minutes. We'll make it a one plane matrix, which is what happened when we changed it to Luma. Char type is fine. And we'll make the size 32 by 24, which is actually, 1/20th the size of the original. And we're going to output this matrix into a list for max, which is an object called jit.iter, which does that beautifully. And out of this comes a list of coordinates and a list of values. So we're going to have just a list of one value, which will be the brightness at that particular cell. For the coordinates, we're going to unpack those. So unpack the coordinates, so we'll get the x out here and the y out here. Eventually, what we're going to stick it all through, so we'll just do a little fast forward here, is an OSCBank. And if we look at the help on OSCBank, it will tell us not much actually. Doesn't tell us what these arguments are for, so whoever made this help patch wasn't thinking of being particularly useful. But the arguments, as it says in the documentation, number of oscillators, frequency smoothing factor, God knows what that means, amplitude smoothing factor, again he probably knows, lookup table size, not sure that that means much, it probably does. Okay. So yes, the tables, well, let's just copy these arguments here. Copy. I'm actually going to make have an oscillator for each matrix cell, which would mean I'm going to have an oscillator bank of 32. Well, you can see I've already just done this calculation, but since this matrix is 32 by 24, I'm going to make my OSCBank 32 by 24, 768 oscillators. So 768 is a good number here, I guess. I don't know if that smoothing factor should be 64. Who knows? And then we'll put this out through a DAC, so we can actually hear it. And I suppose that doesn't need to be on to start with. So we can now take this is going to be our magnitude or amplitude. We'll see that that's this inlet here. It's going to be a one. This is going to be a value 0 to 255, which is going to be wicked loud, especially if you get 768 oscillators going at 255. Magnitude is going to be louder than the average. So I'm going to multiply this by 0.0001, which is quite a huge decrease in size. And I'm also going to want to use these values, which are the x and y, where the cell is in the matrix, to drive both the index and the frequency. I'm going to make the frequencies all multiples of some fundamental frequency, therefore, i.e., they are going to be harmonics of a fundamental frequency. So to make a number range that starts off going 0 to 32 out here, 0 to 31 out here, and 0 to 23 out here. To make a number line that goes 0 to 767, I'm going to want to multiply one or the other of these things, but this one here, the y by 32, so 0 to 31 comes out, times 0, or plus whatever, 0, yeah, okay, and then plus 32, so I think you'll sort of see that you can create this number. This should be this. All right, so that'll be coming out of here is going to be the numbers 0 to 767, and that's my theory, and I'm sticking with it. So that'll be good for our index. For the actual frequencies, I'm guessing we're going to want to make well, we're not interested in a frequency of 0, so I'm just going to add 1 to that and multiply it by the fundamental, which I'll say 50. So we'll have oscillator frequencies at multiples of 50 Hertz. That should be good. All right, let's just see how this thing sounds, I guess. So there's our thing. Beautiful. Let's just look at a different way of doing exactly the same thing. Instead of using converting the jitter matrix into a max list, we can convert that just keep it straight in the signal world using an object called jit.peak, which, if we look at its help, we can see that it uses signals to read through a matrix, a named matrix. So this is named bar, and this is reading the matrix named bar. Its arguments are a number of dimensions, which are normally 2 because you have an x and y, and the number of planes, which in this case is 2, and you can choose which plane. Oh no, hang on. Number of dimensions and which plane, yes, which plane it's actually reading from. So this would be plane 2, so in this case that would be green, blue, I guess. No, green. Okay. Green, blue. Okay. So we're going to keep the same number of dimensions. So it's 2 dimensions, the x and y, and we're going to read from just the 0th plane, which should be the only one that we're dealing with in Blammo because it only has the one plane. All right, great. So you can do the same thing as what they just did there, which is use phasors to read through this thing, give some frequency to the phasor, and multiply. Hang on, this didn't give us. How come it didn't give us number of dimensions? Oh yeah, we need to give it a number of dimensions. Name, sorry. So I've named my matrix Blammo, so that looks like a good name for this thing. And to read through on the x, since the x ranges from 0 to 31, or it's a, we can read through that in this, that's 0 to 32, 31. And on the other side, I like to use a slightly different frequency for reading on the y-axis. If you use the same frequency for reading on the x and y-axis, you're basically reading diagonally through the matrix without reading columns and rows. And again, this is going to want to be 424 because that's how many cells we have on that dimension. Okay, we can do the same thing as we did over here, which, you know, this is probably going to start looking very superfluous, but we're going to multiply that signal from the y by 32 before adding these things together, plus, so we're going to add that with this. So that should be our index. So again, we can just duplicate this OSCBank here, and we'll use that for our index. And then again, as we did over there, we can plus add 1 and multiply by 50. Multiply by 50, and that should be our frequency setting. And then the magnitude is coming straight out of here. Yeah, except I suppose we do again want to scale that down a little bit. I don't think it's 0 to 255 once you read it through the JIT.P, but we'll see. You'll either go deaf or not. I guess I shouldn't warn you like that. That doesn't sound fair. Alright, so this should make something kind of similar in terms of sound if we turn this on. The only difference, the main difference that you'll hear is that you hear the kind of little wobbly little orbs according to the frequency that you're reading through using JIT.peak. That's kind of an added bonus, I think, of doing it this way, because you get some kind of rhythmic activity based on the frequency of this phaser, or this phaser. Well, both really. But yeah, you can sort of sync this frequency up to your tune that you're looking to write, and that should be all good. I'll just do one last little thing here as a way of demonstrating what you might do with this after the fact. Well, you might be interested in recording this for posterity, so we'll use a JIT.VCR with a 640 by 480, and we'll use the audio from our OSCBank. We'll record that, and we will, that's for left and right in the stereo world, and the video we're going to record is straight from this, so it's the full size video. We might want to, well, we're going to use the message write, so we can write something called, let's call it scooby.mov. When we click this message, JIT.VCR will go into its writing mode, and it will just write until we say stop, which is kind of important because it'll fill up your entire hard drive, especially without any extra arguments on the write message. Is you're going to be writing like raw, I think it's, I don't know if that's the default, but you're going to be writing pretty massive sized video. The other thing we probably want to do is to sync it up so that when we start writing, we set the time of the QT movie to 0, just to make everything like synced up in case you're going to the Final Cut later and do something groovy with this. Alright, that's about the 20th time I've used the word groovy. We turn the audio on, start to write, and it doesn't look perfectly synced up, doesn't sound perfectly synced up. The video will probably look better than this sounds, but that's all gravy. Yeah, stop. Don't forget to hit stop on that thing. Alright, so that was it for 13. Nothing really horrible happened unless you, yeah, like anything, this could have been as horrible as you like. Alright, cheers.